In fact, that's what we're working on today, but I need to catch up a little bit. So I'm going to talk about gases. I want to finish up chapter 6 today so that we can start chapter 7 tomorrow. And and then I need to finish up the chapter 5 redox today as well. So where did we leave off last time? Do you guys remember this slide here? Oh, the Maxwell-Boltzmann curve? Okay, thanks. So we're in kinetic molecular theory. Oh, that's right. We talked about the Maxwell-Boltzmann curve. This one here. And then we talked about treating the entire population equally, or right? And so that meant if we slowed down the fast ones and sped up the slow ones, then everybody would have a speed of u RMS. And what does u RMS stand for? Did I talk about the RMS, or I haven't gotten there yet? Not the RMS? Okay. You know, if we speed up the slow ones and slow down the fast ones and gave everybody the same speed, you would think it would be the average speed, but it's not. What it is something called the RMS speed. RMS stands for root mean square speed. Root mean square is kind of strange. But statistically, what we think of is it's the effective speed of the entire population. So we can think of this, even though it's a distribution, we can think of this as having a bunch of molecules at this effective speed for entire population. The mean we don't really care about, nor the average. It's the RMS that we care about. And the RMS is on the shoulder here. It's going to be kind of biased because we have what's called a high energy tail here. It's not, in other words, it's not a symmetric bell-shaped curve. It's got this high energy tail on the end. What's handy about having the RMS speed is that, you know, since we have a distribution of speeds, it's easier just to talk about the speed in terms of the RMS. So for example, if we look at oxygen, this is oxygen at 273 or 0 degrees C. And the URMS is on the shoulder over here. But what happens if you increase the temperature? If you increase the temperature, the whole population shifts to higher energy. But there's still low energy. There's still higher energy. It's just that the distribution changes. The population remains the same, so the area under the curve is the same. And so that's why it shrinks here as it's being pushed to higher and higher. And so the easiest marker for this is the URMS has increased. So if we are down at 273 and we increase the temperature to 1000 Kelvin, the RMS speed has increased significantly here. If we look at hydrogen, hydrogen has a very high RMS speed even at 0 Kelvin. So why is hydrogen so much faster than oxygen? And the reason why hydrogen is so much faster is because it's a lighter molecule. And so let's take a look at some calculations based on this. So if we go back and look at the would be the Maxwell-Boltzmann equation here. We're not going to do any calculations with this, but this equation models a Maxwell-Boltzmann distribution. The mean we're not going to bother with. The average we're not going to bother with. What we're interested in is the RMS speed. And if you look at the RMS speed, it's a lot easier because root mean squared means you have to square each individual speed, then average those, and then take the square root of that. It's a hassle. This is much easier to calculate. All we need here is R, the gas constant. R is going to be 8.3145 joules per mole Kelvin. T is the Kelvin temperature. And M is the molar mass. In units of kilograms per mole. In order to use this equation, we have to know the definition of the joule. The joule is defined as a kilogram meter squared per second squared in base SI units. And then we can use this. So let's go ahead and calculate the speed of oxygen here. Oh, this is how we can measure it. You can measure it using this. This thing's going to segregate things. Depending on how fast it's rotating, it'll segregate the population based on speed. You know, who can make it through the first slit, who can make it through the second slit. And then you just change the speed of rotation, and then you can generate a curve like this, which is a Maxwell-Boltzmann distribution here. Curve.
When you said evacuated vessels, does that just mean a vacuum?
Yep.
No longer be evacuated vessels.
I'm sorry? Yeah, we need a vacuum here so that the molecules can travel in a relatively straight line. If it's not a vacuum, then what happens is there are a lot of collisions. Yeah. So the RMS speed calculation is not so difficult. If we want to calculate URMS for oxygen at 273, then we'll take the square root of 3 times R, 8.3145. Except in this case, I'm going to use the units kilograms meter squared per second squared for joules. So that's joules per mole Kelvin. And then the temperature here is 273 Kelvin. This is going to be divided by the molar mass in kilograms. And so oxygen is 32 grams per mole. 32 grams per mole is going to be 0.03200 kilograms per mole. So I'll just move the decimal over. And so this is kilograms. And then I'll take a look at the units here and make sure the units cancel out. So the kilograms cancel the kilograms here. The Kelvin cancels this Kelvin here. The moles cancel here. And that leaves me with the units of meters squared per second squared. And then I take the square root of that, and that's going to give me meters per second. And so I'm going to go ahead and calculate this here. So it's going to be 3 times 8.3145 times 273 divided by 0.032. And then take the square root of that. And I get 461.30 meters per second. Meters per second. I'm going to convert this into miles per hour. And so if I do this, there are 100 centimeters per meter. And then in 1 inch, there's 2.54 centimeters. And then in 1 foot, there are 12 inches. And in 1 mile, there's 5,280 feet. And then that converts meters into miles, and then seconds into hours. Would be there's 60 seconds per minute, and then there's 60 minutes per hour. And so, oops. So take this times 100. Oops. Divided by 2.54. Divided by 12. Divided by 5,280 times 60 times 60. And so this is equivalent to 1,031.9 miles per hour. So about 1,000 miles an hour. And so but that's at 0 degrees C. At 25 degrees C, it's going to be moving even faster. And so if we take all the oxygen molecules in this room, they're moving, and we sped up the slow ones, slow down the fast ones, then collectively that population would have a speed of over 1,000 miles an hour. Do you feel it? I mean, in a way you feel it. You feel like 15 pounds per square inch. You know, you would feel like if that 15 pounds wasn't there, you'd feel it. You know, it's like those suction cups. If you have a suction cup on your skin, you'd feel it because you're missing that 15 pounds per square inch. Or a vacuum. You know, if you took a vacuum and put it on, you'd feel it. You'd feel it missing is what you'd feel it, because we're accustomed to having 15 pounds, but that's what generates it. I'm sorry? 3 times. 3 times. Yeah. Where does that come from? That comes from the kinetic energy. In an ideal gas, we only have one type of kinetic energy because we're looking at point masses. So the only thing a point mass can do is travel from point A to point B. That's translational energy. A point mass does not vibrate or nor rotate. And so, and then we have 3 dimensions, X, Y, Z. And so this is where this kind of stuff comes from. But we're not going to worry about the derivation of this equation at all. And so that's it there. One of the most important things for our URMS is to determine the average kinetic energy. The average kinetic energy is given the symbol. E bar is the average energy, and K is kinetic. So this is the average kinetic energy here. Looks like the average kinetic energy is equal to 1/2 m, and u, this is the average speed squared. But this is not exactly correct here. If we want the average kinetic energy, then what we do is we do it this way. This is just equal to 1/2 m u RMS squared. Where m is the mass of a single molecule, or it's not always molecules, sometimes it's atoms, sometimes it's ions. So I'm just going to say it's going to be the mass of a single particle. in kilograms. URMS is the effective speed. This comes from Newton's law. Newton's law has an equation for energy. E is equal to 1/2 mv squared. So if I wanted to calculate the kinetic energy of an object moving at some speed, I'd use this equation. I'd need to know the mass of the object, and I need to know the velocity of the object. The mass is usually in kilograms, the velocity is in meters per second squared, so kilograms times a meter squared times per second squared is a joule. So this gives me the energy in joules here. Velocity means the speed, and so V and U are the same. I don't know why our book doesn't use V. And so we could determine the kinetic energy of the members of the population from the low energy to the high energy. Or we could just treat the population as having some effective speed and then just get the average kinetic energy. Mm-hmm.
Where it says effective speed, what units would it usually be in?
I'm sorry?
Where it says effective speed, what unit would it be in? Like,
Meters per second. Meters per second. All right, let's go ahead and calculate the average kinetic energy of O2 at 273 Kelvin. And so that's going to be 1/2 the mass. This is what this is all about here. We need the mass of a single oxygen. And so there are two ways we can get it.
Do we use grams or joules?
Says in kilograms.
We could do it in U. You know, what is the mass of a single oxygen molecule in U? 32.00 U. And then we could convert that to grams. Do you know how to convert it into grams? Do you remember this conversion factor? And then we'll convert it to kilograms.
Are these units we actually use?
You can. They didn't. If you do, the way they did it is this. They used 32.00 grams per mole. And then they converted grams to kilograms, and they converted moles to particles. Which we could do here. We'd end up getting the same answer. And then we need the speed. The speed we had calculated on the previous slide, so let's see what the speed we calculated was. 461.3 meters per second. So I'd use that here. 461.3 meters per second. That's the RMS speed squared. And so what's the energy going to come out to? Let's see what it comes out to. So I'll do 1/2 or 0.5 times 32 divided by 6.022 times 10 to the 23rd, divided by 1,000 times 4.61. Oh no, not 4.61. I'll just do it. 4.613 times 10 squared. You don't have to convert that into scientific.
Why is u squared in this equation? Like physically.
Why is it squared in this equation? Because some of these relationships come from the dimensions. If you want energy, then velocity, speed is related to energy, but it's not the same thing. And so one of the things you could do is you could just do dimensional analysis. You'd have to square u in order to get the energy. You could try to get it other ways. There are other ways of visualizing energy. But the interesting thing is this. Hydrogen's moving at a much faster speed, but does it have more energy? No, it doesn't have more energy because it's so light, you know. And so you could have a heavy object moving slow, have the exact same energy as a light object moving fast. But it's squared because to relate it to joules, we need to square it. And so assuming I did the calculation correctly, I get 5.6538 times 10 to the minus 21 joules. Joules is a kilogram, meter squared, per second squared. If you look at this, this is a very small number. Ten to the minus 21 is a very small number of joules. But you have to recognize that this is joules per molecule. If I had a mole of molecule, I'd multiply that by 6.022 times 10 to the 23rd. And that comes out to 3,000. 3,000 joules for a mole of oxygen molecules. A mole of oxygen is about 22.4 liters STP. Why do we care about the average kinetic energy? You know, because we're going to have a distribution of energies. We care about the average kinetic energy because the average kinetic energy and temperature are related. In other words, the way we think about it is temperature is directly proportional to the average kinetic energy. Here. So this oxygen over here, which has this population distribution for speeds, and this hydrogen sample over here, which has this population distribution of speed, have totally different shapes of the, well, actually they're the same shape. They're the Maxwell-Boltzmann shape, but they have totally different distributions as far as the min and the max go. And then we look at here, they're at the same temperature though. So if they're at the same temperature, then they both have the same average kinetic energy. So anything at the same temperature will have the same average kinetic energy. So the air in this room is at room temperature. The water in this bottle is at room temperature. So the air and the water have the same average kinetic energy. But they're going to be moving differently because they weigh different amounts. The plastic is at room temperature. So it's going to have the same energy, but it shows it differently. Because what plastic, it can vibrate, but it can't rotate or translate. The wood in this table, everything you touch at the same temperature will have the same average kinetic energy, but not necessarily the same speed. That'll be different. Okay. There are a couple of more things that we are interested in kinetic molecular theory that aren't discussed here. One of them I asked ChatGPT to calculate.
Do we trust that?
Yes.
Yeah. Yeah, I mean, not everything is. But this is pretty standard calculation, so it should be all right. So we have this picture of gases, and we have particles, and those particles are moving around. And they travel great distances before they collide with things. But what is great distances? If we're at 1 microatmosphere, then we have something called the mean free path. The mean free path is how far it travels before colliding with something. And so if you have gas, let's say we're tracking an oxygen here, how far does it travel before it collides? And if we look at the average distance, that's called the mean free path. And this is in meters. So for a microatmosphere, an oxygen will travel 7 centimeters before it collides on average. 7 centimeters might not sound like that big of a distance, but that's a huge distance compared to the size of an atom. How big are atoms? Or is it? Well, let's go on. So we can see as the pressure goes up. If we go to 1 atmosphere, how far does the particle travel before it hits something? This is about 7 times 10 to the minus 6. This is about 700 times 10 to the minus 6. 10 to the minus 6 meters is a micron. So this particle, this gas particle, travels 700 micrometers before colliding with something. Is 700 micrometers that big?
I'm not sure. What does lambda represent? I don't know what that means here. Is that a statistical thing?
It's like, what does V represent?
Oh, it's like the average distance.
Oh, you mean what does the mean free path represent?
Yeah.
The lambda is the mean free path.
Okay.
Mean free path is how far the particle travels on average before hitting something
In meters.
in meters. This answers your question. Why do they have to do it in a vacuum? Why they have to do it in a vacuum is, if they didn't do it in a vacuum, how far does that travel before it collides with something? You don't want it, if you have a perfect vacuum, then it just travels. It goes on indefinitely. It's not going to hit anything.
And this is determined by statistics. Right? It have to be.
The mean free, no, this is just determined by, statistics because we're calculating the mean, but it's determined from the the equations of kinetic molecular theory. You can calculate how far things can travel before they hit something. Statistically, if you take it, things moving in random directions, every which way.
Are these calculated with outliers or no?
I'm sorry?
Are these means calculated with outliers or do they?
Yeah. This looks at the entire population.
It's not calculated from like a data set of of different collision lengths because that would be almost impossible to measure. Is my understanding is that we have the models to understand when why a path would be so long. It's because it just so happens to be a thing. So I'm pretty sure that this is the mean based on what
I mean, this is the equation for the mean free path. We're not going to be doing any mean free
We don't
path
know that
calculations.
for this.
But we factor in things. How fast are they moving, i.e. temperature? How big are they? What's the pressure? This kind of thing. So at 1 atmosphere, under normal conditions, how far does an oxygen travel on average before it hits something? How far it travels is about 700 micrometers. Is 700 micrometers all that big? No. But compared to the size of an atom or molecule, is it big? Yes. Because atoms are about what size roughly? Well, we can go down further. What if we go to 10 atmospheres? If we go to 10 atmospheres, we're compressing the gas. And at 10 atmospheres, how far does it travel before it hits something? Yeah. Which is about what?
God, I don't remember the. Is it what is it about?
Yeah, 7 nanometers. Yeah, 7 nanometers. If we go to 100 atmospheres, how far does it travel before it hits something? Roughly, on average. 7 times 10 to the minus 10. 7 times 10, do you guys recall what 10 to the minus 10 meters is called? 10 to the minus 10 meters is called an angstrom. And I don't know, did I talk about angstroms? Angstroms are, people are saying to get rid of angstroms. But I still like angstroms because it's easier to remember the size of atoms in angstroms. How big are atoms in angstroms? Okay. So at 100 atmospheres, well, we're predicting this. But this, this is approaching. If GPT did this correctly, then this is approaching the size of an atom because atoms range from 1 to 6 angstroms in size, and this is 7 angstroms. Or in picometers, how many picometers is that? That's 667 picometers. Pico is 10 to the minus 12. Angstroms are between 100 and 600 picometers in diameter. So this is like, is that very much free space there? No. But in ideal gas, the atom size is non-existent because these are all point masses. The point masses have 0 size, 0 volume. So I suppose it's still, compared to 0, it's still pretty big. But sometimes we want some numbers there to associate this with, because the mean free path is getting quite small. Okay, the other thing is, if we know the mean free path, we can calculate something called the collision frequency. The collision frequency is how many collisions occur in 1 second. And so this is in hertz. And so if we look at, when we're at 1 microatmosphere, we have 7,000 collisions per second. If we go to 1 atmosphere, how many collisions per second do we have? You see, we have 7 billion collisions per second at 1 atmosphere. If we go to 10 atmospheres, what do we have? About 700 billion collisions per second. And so when we're looking at the simulations, what we call the molecular dynamics videos, those were slowed way down because the collisions were happening very slowly. Normally we would have expected something on the order of 7 billion collisions in 1 second. Can you visualize that, 7 billion collisions happening in 1 second? It may be hard to visualize. No, collective, the whole population.
Obviously, obviously.
Yeah.
Wait, for how much? How much?
Pressure you have.
But won't it? Wait, so you said it's not per atom, the collision number, right?
The collision frequency,
Yeah.
not per atom, right?
So if it's per pressure, isn't that dependent also on an amount of molecules?
Yeah.
So that's given comments.
So it would be for a given volume. The given volume, usually in SI units, the given volume is a meter cubed.
I think
All right, so that's just a little bit of kinetic molecular theory. And then here's a little bit more of kinetic molecular theory. You know, Boyle's law, originally Boyle derived Boyle's law from theory or from observations. Boyle's law came from theory or came from observations? It came from observations. You know, Boyle just took some measurements, saw a curve, and then modeled that curve mathematically. But these laws we can derive in two ways. We could either derive it from observations on the left, or we could derive it from theory, you know, on the right. And so this section here talks about the theoretical derivation of Boyle's law using kinetic molecular theory. Theory should be able to confirm this.
if he was able to derive that from theory at this time, I think he would have had bigger deals.
Yeah, sure. And so here's the derivation of Boyle's law from a theoretical starting point. You could also derive Charles' law, Avogadro's law, all the other laws, theoretically. I'm not going to bother with this. If you're interested,
What's like the super
read it.
cutting edge laws of stuff that we've noticed, but we don't have a theory for yet, besides aspect
Well, if there's some cutting edge law, then what you want to do is you want to develop the theory for it. So you're constantly trying to correlate the theory with that particular law. The law being some observation. That's known. All right, so here's one more application of kinetic molecular theory. One more application is this. On the top part, we have something called diffusion. So if we remove the barrier, so we have hydrogen on the left, nitrogen on the right. If we remove the barrier, what's going to happen? The gases are going to mix. And eventually they'll be completely mixed like this. Now, if the temperature of the gases before, let's say is room temperature, and the temperature of the gases after mixing is room temperature, then the temperature doesn't change. If the temperature doesn't change, then there's no change in energy. Normally when we think about driving forces, the driving forces that we look at are going from energetically unstable to energetically stable. That's favorable. We want to go downhill in terms of energy. But in this case, we're not going downhill in terms of energy. The energy is staying the same. And so a question comes up, if the energy stays the same, then what's driving this mixing to occur? You know, and you might think, obviously, the molecules are moving and there's nothing to stop them from moving. But in terms of driving force, we want to think about that because our driving forces so far have looked at energy. But it turns out there's one more driving force that we need to consider. Do you know the other driving force that we should consider in nature? So nature tends to go from higher energy to lower energy. That's favorable. But there's one other thing. Let's say the energy stays the same, or even if the energy goes up. Even if the energy goes up, it still might happen if there's something else driving it. And you know what that something else that drives it is called? Hmm? Not magic. Not magic. A lot of people know this. I mean, it's like if you have things all neatly organized, everything's put away in the right place, and then you come back later and it's entropy, right? It's a mess. there's this person who had another person work on their car, and the other person disassembled their engine, but ended up losing a whole bunch of parts, and everything was a mess. So it's going to be really hard to put back together, but it was probably really easy to take apart. You know? It's not easy to take apart? Yeah, all right. Yeah. Well, anyway, this is entropy driven. Entropy is going from a state of more order. So this is more ordered. The hydrogen on the left, nitrogen on the right, to a more disordered state. And so this would be entropy driven here. This is a different process here. Here we have a vacuum, so there's no gas here. And then what we do is pop a pinhole there. When we pop a pinhole, then the gases can escape out of the pinhole. This process of escaping out of the pinhole into a vacuum is called effusion. So up here we have diffusion, down here we have effusion. And so let me give you some examples of diffusion. Diffusion might be, let's put a mint molecule. Let's say you're brewing some mint tea, or you have some mint gum or something, and there's some mint molecules coming off that. And the mint molecules, when they hit your nose, you can detect it. It smells like mint. And so let's say somebody has some mint tea, and they're drinking mint tea down here. And the nitrogens are moving at over 1,000 miles an hour. And the mints are heavier. The mint molecules are moving about 500 miles an hour. So if somebody is over here in this corner, how long does it take for mint to travel to that corner of the room, moving at 500 miles an hour? Well, we're going to look at that, but how long it takes to move over there at 500 miles an hour, it doesn't take long, right? But if somebody's drinking mint tea over here, do you smell it instantaneously over there? No, you don't. And that's because of diffusion. And when we think about diffusion, we have to think if a mint molecule starts here and wants to end up here, it's not a straight line, unless it were a vacuum. If it were a vacuum, you'd smell it instantaneously. Because 500 miles an hour to travel this distance takes no time at all. And so if we were in a vacuum, yeah, that molecule would be detected right away. But if we start off here, it takes a long time for that mint molecule to travel up to here at 500 miles an hour. Why?
Traffic.
Yeah, lots of traffic. And so when we look at it, that mint molecule is going to experience something of a mean-free path of about what would that be? 10 to the about 700 micrometers before it collides. So that mint molecule, on average, will have the first collision in 600, 700 micrometers. Is that very far? No, that's not very far, because how many micrometers does it take to get from there to there? That's a huge number. And not only that, how many collisions per second will that mint molecule experience? It's going to experience, if we're looking at 7 billion collisions per second occurring, it's going to experience collisions at a very high frequency. And so what we say is, even though that mint molecule is traveling at 500 miles per hour, it's got to travel a long, long distance before it reaches the other side of the room, because what's going to happen is, it's okay, it starts off here, then collides here, goes backwards, and then collides here, goes sideways, and it's going to have some kind of crazy zigzag path until it makes it over here. And so that's diffusion. Now, if it were lighter, it would diffuse faster. So if we have hydrogen over here, hydrogen's moving at 2,000 miles an hour. And so it would make it across the room a lot faster than the mint molecule, which is only moving at 500 miles an hour. All right, so what we say is this. Because of all the collisions, We're not going to model this with any equations here. This is a lot simpler because there are no collisions. You know, this hydrogen escapes or the nitrogen escapes. You know, there aren't that. We don't have to worry about going backwards, sideways, or whatever. And so this is called diffusion, and we have some equations for diffusion. For diffusion, we just look at it qualitatively. Diffusion qualitatively is the lighter the molecule, the faster it diffuses. So the hydrogen is going to diffuse very rapidly to the other side. It's going to take nitrogen a little more time to make it to the other side. It's heavier. It's heavier. We can do this quantitatively because we don't have to worry about all the collisions and whatnot. And so this is much more quantitative. And so we can come up with the equation for effusion here. And normally what we do is we compare two things for effusion. What should we do? Do you want to do mint versus air, or do you want to do oxygen versus hydrogen? Oxygen versus hydrogen? Okay. Which one will be faster? Hydrogen or oxygen? Hydrogen. So we'll just do a quick calculation here. What we know is hydrogen is going to be faster. What we want to know is how many times faster. And so we do the rate of hydrogen over the rate of oxygen. I'll ignore this. And that's going to equal this. It's going to be inversely proportional to the square root of their molar masses. So we'll look at the molar mass of oxygen here, or the molar mass of hydrogen here. And so we look at the molar mass of oxygen is 32, the molar mass of hydrogen is 2. So in other words, oxygen is 16 times heavier. If oxygen is 16 times heavier, does that mean it's 16 times slower? And hydrogen is 16 times faster? No. What it means is that hydrogen is only 4 times faster. And so when we're looking at diffusion here, the hydrogen is going to diffuse 4 times faster out of this pinhole than the oxygen.
And this mixing is caused by the collisions making it.
The mixing up there, yeah. But here we don't have any mixing. There are some assumptions we make for this to work out. Otherwise we'd have to factor in the mixing. These are the assumptions we made. Only for gases at low pressure, so this.
Wait, where do you define that? That's how big is a pile, isn't it?
What?
Only for gases at low pressure.
And then there's a tiny orifice, so there's no collisions within the orifice. And then does not apply to diffusion, because if it applies to diffusion, then you have to worry about all the collisions and whatnot. And so we're just trying to make it simple. This is. Is this useful? Yeah. Really useful. This is called Graham's law. Graham's law of effusion and diffusion.
In the equation, why do you switch O2 and H2?
It's inversely proportional. The heavier it is, the slower it moves. The lighter it is, the faster it moves. So it's inversely proportional. If one side's big, the other side's small. So that's why it's flipped.
Okay, so the line always goes on the bottom, or it just...
I'm sorry?
Does the line marker always go on the bottom, or...
No. If I flipped it, it would be 1/4.
Oh, okay.
So it's 1/4 is fast. You know. And so oxygen, if I put oxygen on the top, I would have gotten 1/4, which means oxygen is 1/4 the speed of hydrogen. If I put hydrogen on the top, I get 4.
Oh, you put oxygen on.
Or did I put? No. Here, over here.
You take the square root of this.
Yeah. We say it's inversely proportional. there's something else that's inversely proportional, and that is the time. If something's moving fast, does it take more time or less time? Less time. So if the speed is big, the time is small. What if the speed is really small? The speed is super slow, then the time is going to be super big. And so that's inversely proportional too. And so we could do another inverse proportionality. The time it takes oxygen versus the time it takes hydrogen to fuse. Let's say it took hydrogen 4 minutes to fuse out of the box. How long would it take oxygen to fuse out of the box? 16 minutes, right? It's 4 times slower. Does that make sense? And so time is also an important factor. I don't know why they didn't put time in this equation too. So let me modify the equation here. And so we're going to have time of A over time of B, which will be inversely proportional there. And so these are the equations. You don't have to memorize these equations. Graham's law is usually, I'll just give it to you. You know, let's say you have an unknown molecule and it's pure. You know how you can figure out the molar mass? Well, if you have an unknown molecule that's pure, just feed it into a mass spectrometer. But let's say you can't afford a mass spectrometer. Is there another way you can do it? Yeah, you could try a effusion experiment, right? And see how many times slower it is, or how many times faster it is than some reference one. And then you could figure out an unknown molar mass, and that could help you identify it.
We could do that. We could do that.
Yeah.
How do we know when it's done? When the pressure's equalized?
No, you'd have to have a way of measuring it, you know. Yeah, or when the pressure is equalized, when it stops. But it's kind of weird because they said no force, you know. That is, they don't want a big differential in pressure, otherwise it creates a jet.
Oh, yeah.
And you could have different types of flow. But it's all right. This equation is, do you want to derive, we could derive Graham's law from kinetic molecular theory. You know, all this type of derivation is very important, but probably not for Chem 1A. For higher level classes, yeah. We'll just skip it. Graham's law was derived from observation, but we can also derive it from theory. This non-ideal gases, this is derived from observations. You know, if we take the ratio PV over nRT, you know, we know PV equals nRT for an ideal gas. So if we take PV divided by nRT, that should equal 1. And so an ideal gas should have a PV over nRT ratio equal to 1. So that's what this dashed line is. And this is called the compressibility factor. But when we look at the data here, then none of these are ideal. Hydrogen, oxygen, and carbon dioxide, these all deviate from ideal behavior. But let's take a look at the X scale. When you look at the X scale, take a look at that. How often do you work at a pressure of 200 atmospheres?
When things go wrong.
Yeah, when things go wrong, terribly wrong, you might be. You don't want to be like in a submarine at 200 atmospheres.
Hopefully things went wrong on the page, on the experiment.
Yeah, that's true. Where do we normally work at? One. And at 1, does it deviate much from ideal behavior? No. In fact, this is 200, so there'd be 200 tick marks. So 1 is right there, and everything looks to behave ideally. So when we're at pressures of 1 atmosphere, things behave pretty ideally. Hydrogen, oxygen, and CO2 behave pretty ideally. But we see significant deviations at high pressure. We also see significant deviations at low temperature. But when we look at these deviations, look at this. this deviates down and then up. And same thing with O2. Down and up, and the hydrogen just goes up. And so what's causing this downward deviation and then the upward deviation here? So let's take a look at the things that make a gas non-ideal. And so what we're going to do is we're going to take this equation, the van der Waals equation. The van der Waals equation just comes from observation. This isn't theoretically derived from kinetic molecular theory. And so looking at the van der Waals equation just takes our PV equals nRT and then has two corrections for non-ideal behavior. The first correction is A. N is just the moles, V is the volume. So this is kind of the inverse of the molar volume squared. But A, the second correction is B. N is the moles and B. And so let's take a look at the volume correction first. The volume correction, ideal gas particles have what volume? Ideal gas particles have zero volume because we're treating them as point masses, zero volume. But is that accurate? No, it's not. And so what we're going to do is we have to reduce the volume by the volume of the particles. So what B is the volume per mole of particles. Just how much space does a mole of these particles take? And so we need to multiply by N, depending if we have 1 mole, 2 moles, or however many moles we have. And that's going to cut down the volume here. So that's B. And so this is the volume of the particles themselves. So if I have a mole of hydrogen, the volume is about 26.5 milliliters of particles. And so it looks like the helium's the smallest. Helium's about 23.8 milliliters per mole of atoms. And so this is the volume of the atoms. What's the biggest? The biggest is propane here. Propane has a volume of about 91 milliliters per mole. So if you have a liter of gas, a liter of propane, you have to reduce that volume of gas by 91 milliliters because 91 milliliters of that gas are the propane molecules themselves. What that does is it restricts the space. If you don't have a full liter to roam free in, you have, let's say, 0.9 liters, then that's less space. Less space means there's going to be more collisions. More collisions means there's going to be more pressure. And so what happens is this volume correction leads to higher pressures. The bigger the particles here, the smaller of the volume term. The smaller the volume term, the bigger the pressure term, because it's got to equal nRT. So helium's the most ideal gas because it's the smallest. So 1 liter of helium is close to 1 liter of empty space. A deals with the stickiness of the particles. If the particles are attracted to each other, they kind of stick. And so they're kind of sticky. And so if you have 3 particles over here and they're attracting this particle here, it's not going to collide with the wall as forcefully. And so these are just electrostatic attractions here, preventing the full collision with the wall. So the stickier the particles are, the lower the pressure. And so out of these, which particles are the stickiest? And so we look at A. The larger the A, the more sticky they are. And the largest A is going to be propane. Propane molecules tend to stick together, reducing the pressure.
Why is the compressibility factor but only for those two?
I'm sorry?
Is compressibility factor for propane
Because propane, something like propane's a big molecule. Big molecule takes up too much of the volume. And so big molecules increase the pressure, but sticky molecules decrease the pressure. So what happens is they kind of self-cancel each other. You have one error that increases, the other error that decreases, and we kind of break even, so it seems like it works okay. But anyway, what are they saying about A? Let's take a look at A and see what they say about A. This is footnote A. At 10 bar, which is about 10 atmospheres, and 300 Kelvin, propane and sulfur dioxide are liquids. And so what this is saying is there's going to be catastrophic failure of these. The catastrophic failure is that they liquefy and they're no longer gases. All these, though, will suffer catastrophic failure at some pressure and some temperature. But these, they calculate the compressibility factors at 10 bar, 300 Kelvin. So that's the reason why. If they went to 1 bar and 300 Kelvin, it should be okay. Here's the volume of the particles. If the particles are really small, then it's mostly empty space, but depends on the pressure. Here, the particles are relatively big compared to the volume of the gas. So there's not much space to move around here. In fact, this looks like a liquid. But anyway, so the smaller the particles, the more ideal. And so what we do for this is we just do some simple calculations. We try to use the ideal gas law most of the time because the ideal gas law is less work. But if we're worried that we're going to get inaccurate results with the ideal gas law, then we'll use the van der Waals equation. Now the van der Waals equation, A and B depend on the gas. How sticky the gas particles are and how big they are depend on what gas you're looking at. And so what we have to do is we can't use one value of A and one value of B for everything. We have to use the value of A and value of B for the molecules or particles that we're looking at. And then we just do the calculation. And so we can get a more accurate calculation with this. Okay. There are other non-ideal gas laws. This is one. There's Virial equations, another, and there's others. All right, that's the end of chapter 6. Finishes with that. And then what I want to talk about is redox next. So let me bring up that PowerPoint here. I don't remember where I put it though. Does this look familiar? I think this is where we left off. Let me just do this. Did we finish this one? Maybe not. But this one, we got no reaction for single replacement, but there is redox. So what I do is, I don't start off with single replacement. Single replacement is a very simple pattern, but there are too many exceptions in single replacement. So what I usually start off with is the chart method. But once you gain enough experience with the chart method, then you can easily see what the exceptions are for single replacement, because single replacement, it fails sometimes because of the way it assigns things. I think I already talked about. Do you guys remember why single replacement fails? Single replacement fails because it assigns jobs to each, or roles to each of the participants. So for example, A goes from the element to the cation. So what happens to A? Loses electrons. Something that loses electrons is called the reducing agent, because it's giving the electrons to the oxidizing agent. And then B goes from the cation to the element. So what happens to B here? It goes from B plus to B0, or B plus plus to B0, B plus 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 to B0. It's gaining. So anything it gains is called the oxidizing agent. And then when we look at X, X is the spectator, because it doesn't appear that anything happens to X. Single replacement failed in this particular reaction because of this. Okay, A is assigned the position reducer. Okay, that's fine. Copper is a pretty good reducer compared to what we have. B is assigned the position oxidizer, and nitrate is assigned as a spectator. But there's a problem. Do you know what that problem is? The problem is nitrate does not want to be the spectator. So B, H plus, was assigned the position oxidizer, and nitrate was assigned the position spectator. But look at the position, relative position. Who is a stronger oxidizer, nitrate or H plus? Who's the stronger oxidizer, nitrate or H plus? Nitrate. Nitrate is a much stronger oxidizer than H plus, as long as we have H plus present. Is there H plus present? Yes. So you're the director of the play, and you assign H plus as the role of the oxidizer, but Nitrate, do you think nitrate's going to be happy? But you tell nitrate to behave and not react with copper. Will nitrate listen to you? What if you yell at nitrate? If you yell at the nitrate and nitric acid, will it stop reacting with the copper? No, it's not. And so you can't control it. Nitrate's going to attack. And therefore, you're destined to fail. You're destined to fail because you assigned the oxidizer role to H plus and not nitrate. And the play did not turn out as you expected. But anyway, let's take a look at how we can fix this. You know how we can fix this? How we can fix this is just let everybody assume their natural role. And how do we let everybody assume their natural role? We just follow the chart method. And the chart method is not going to make some prior assumption. You know, this person's got to do that and that person's got to do this. So in the redox chart method, what we do here is we inventory the species. And then out of all those species, we find the strongest oxidizer present and the strongest reducer present. And then we allow those two to react because that's going to be the most likely reaction. The most likely reaction will be between the two strongest. It's not to say that there's going to be a reaction because there might be no reaction if there's no driving force. But we'll do that. And then we'll do this cross multiplication step and then add and simplify and then look for a driving force. The driving force for redox is stronger oxidizer to weaker oxidizer and stronger reducer to weaker reducer. This is the driving force. And this yields the NIE. So let's just do an example of this here. So the chart method, we're going to inventory. So the inventory is going to contain copper metal, H plus, nitrate, and there's one more thing present. Do you know what the one more thing present is? Water. Then we're going to go to the chart and look. Copper occurs on the right side of the chart only. The right side are the reducing agents. H plus occurs on the left side only. That's an oxidizer. Nitrate occurs on the left side, but we need H plus in addition to this. And so that's an oxidizing agent too. So we have oxidizing agent as H plus alone, or oxidizing agent as nitrate and H plus. And water occurs on both sides. And so it's an oxidizer or reducer, depending on what you react it with. Then we're going to pick the strongest. So we go to the chart again and look for the strongest. Let's go to the oxidizer. Nitrate is a much stronger oxidizer than H plus, and a much, much, much stronger oxidizer than H2O. H2O is fairly weak. And so what we're going to say is nitrate is the one that's most likely to act. And so single replacement predicted nitrate is going to be a spectator. No, it's not. Nitrate's going to react, and we just take the reaction off the chart. So nitrate plus 4H plus 3 electrons yields NO gas, nitric oxide, plus 2H2O liquids. And so this is my oxidizer here. If I look at the reducers, copper is a better reducing agent, so it's closer to lithium than water. But for copper, what I have to do is I have to reverse the equation, because off the chart I have copper 2 plus 2 electrons yields copper metal. But we see here copper is not a product. This shows copper as a product. Copper is a reactant. So what I need to do is I need to flip this equation around so that copper solid is a reactant, and that's going to go to copper 2 plus, the product, plus 2 electrons. The next step is I cross multiply. So I have 3 electrons here, 2 electrons here. So what I'm going to do is I'm going to multiply the first equation by 2. So double everything. And then I'm going to multiply the second equation by 3. So triple everything here. And we do that so that the electrons cancel. I have 6 electrons here, and I have 6 electrons here, and we need them to cancel. All right, so now what I'm going to do is I'm going to combine everything. So I have 2 nitrates plus 8H plus 6 electrons plus 3 coppers, solids, is going to yield 2NO gas plus 4H2O liquid plus 3Cu2 plus 6 electrons. And then I simplify. So I see I have 6 electrons on the left. That's going to cancel the 6 electrons on the right. And then that looks like it. But before I go on too much further, I want to check if there's a driving force. To determine if there's a driving force, we look. So this is the OA. And then we say that this is the conjugate RA. This is the RA. And on the product, we'll have the conjugate OA. And so nitrate and H+, this will be our oxidizer on the left, and copper 2+ will be our oxidizer on the right. So which is stronger, nitrate or copper 2? So we go back to the chart and look up nitrate versus copper 2. And we can see it here. Nitrate with acid is stronger than copper 2. So we're going from stronger to weaker. And that's our driving force. Because of the conjugate relationship, this means that copper metal must be a stronger reducing agent than NO and water. This must be a weaker reducing agent. And so we have reaction. And so the last step would be just to clean this up. So let me write it up here since I ran out of room in there. So I have 2 nitrates plus 8H plus 3 coppers, 2 NO plus 4H2O plus 3 Cu2 pluses. So what we're left with is the NIE. And so the chart method yields the NIE. If I want the CE and the IE, I'd have to work backwards to get it. But normally we just want the NIE anyway, so it's all right. Are there any questions on this one? Let's do another example here. Potassium and sodium chloride. Potassium is metal, sodium chloride is aqueous. Yields what? You look at this, what does this look like to you? This looks like an A plus BX. It's going to yield AX. What's AX? Potassium chloride plus B, sodium metal. In single replacement, we look at the activities. And so we look at the active. The activity series is on our chart here. This is the activity series from Chem 4. The most active is lithium, and then it goes potassium, calcium, sodium, magnesium. So the activity series is like this, with the top here. And so when we compare potassium's activity to sodium's activity, potassium's more active. And so what we say is we're going from more active element, potassium, to a less active element. And we call this driving force. The activity series is just the reducing agent strength. And so more active element just means stronger reducing agent to weaker reducing agent. That's what we're doing in the activity series. So we have a driving force, so we have reaction here. There's going to be a redox reaction. But do you know what? You know, this is wrong. That's wrong. And so what we're going to do is we're going to try the chart method. Although this is correct, you know, it's the wrong reaction. So we'll try the chart method here. And so the first step in the chart method is I'm going to inventory the species, the major species present. And so I'm going to have potassium solid, I'm going to have sodium ions, I'm going to have chloride ions, and I'm going to have one more. What's the one more species? Water. And then I'm going to look at the redox chart. On the redox chart, this is on the left side, so that's a reducing agent. Sodium ions are on the right side. No, this is on the right side, sorry. Potassium is on the right side, it's a reducing agent. Sodium ions are on the left side, it's an oxidizing agent. Chloride's on the right side, it's a reducing agent. And water's on both sides, so it's both an oxidizing agent and a reducing agent. And so I have two oxidizing agents here. Sodium ions versus water. So let's take a look at the chart and see which is stronger. Sodium ions or water? Actually, maybe I should get the chart off here, so I don't have to keep zooming and zooming in and zooming out. Here's sodium ion. Where's water? Oh, I know where water is. Water's way down here. So are sodium ions or water stronger? Are sodium ions or water stronger? Well, which one's higher up, sodium or water? Sodium's higher up. In other words, it looks like water's the worst, doesn't it? Because this is the bottom. But is it really at the bottom? No, it's not really at the bottom. You know where water belongs? I have to look at this number, minus 0.8. Where does minus 0.8 fit up here? It fits between here. Do you see that? So if I go minus 0.8, do you see these three dots? These three dots are purposely put there because that's where water belongs. And so if water belongs where these three dots are, then which one's stronger, water or sodium ions? Water. So as far as the strongest oxidizer is not sodium ions. The strongest oxidizer is water. That's the strongest oxidizer present. What did single replacement predict as the oxidizer? Sodium ions. You see that? What's the strongest reducer? So we have three reducers: potassium metal, chloride, and water. So we're going to go back to that. Actually, I'm going to go back to this chart in here because I need to mark something up. So the strongest reducer is lithium. And then take a look. What's number two? Number two is Potassium metal. So potassium metal is the strongest reducer present. But what else is present? What else is present is chloride and water. So let's rank chloride and water. Which one is stronger, chloride or water? So I go up here and I look. Here's water, but we're missing something. What are we missing? Sulfur dioxide. Keep going up, keep going up. Here I have water, but we're missing something. We're missing nitric oxide. So I keep going up. Here's water, and I could use this. So water appears to be number 2. So potassium metal is the strongest, followed by water, and then I'll keep going up. And then I'll see chloride here. So it looks like water is stronger than chloride. However, there's an exception. Chloride versus water. Water, no, not water wins. We expect water to win because it's stronger. But do you know who wins or who loses? Chloride wins the losing game. The losing game is the electrons. And this is the reason why. If you're an oxidizer, it's easy to oxidize chloride. You just take it from the outermost shell. So chloride has shells like this. Oxidizer comes along, it just plucks an electron off the outermost shell. It's just a ball. If you're water, it's a lot more complicated, because if you're water, the oxidizer has to come in and pluck the electrons off oxygen. Plucks off the electrons off oxygen, we form O2 gas. But you got to break bonds, and it's a bit more difficult. And so this is like a trade-off, you know. In nature, sometimes nature will take this trade-off, and the trade-off is something like this. Let's say you can earn $10 now, or $11 50 years from now. What would you do? Would you take the $10 now or the $11 50 years later? Let's say there's no inflation, so $11 means something.
There is inflation, because we'll probably have more money later.
Yeah, there would be.
Economics less.
There would be. Or what would you rather do? What would you rather do? Just a simple job for $10 an hour, or a big headache and a complicated job for $10.25 an hour? You know, you say, oh, I'm definitely going to take the $10.25 an hour. But let's say it's really stressful and a lot of work, versus $10 an hour for something that's easy and not a lot of work. What would you rather do? Would you take the more money? But you have to invest more? You have to break bonds, take electrons from oxygen? Or would you take the easy way out? Just take the... Well, what do you think nature does? Oftentimes nature will take the easy way. Even though it might be more profitable in the long run, it doesn't usually wait. You know, what happens is a bunch of collisions, and it doesn't usually wait. So just take the easiest way. And so this is what leads to the exception. Water would be more profitable in terms of energy. But chloride is much faster, much easier. And so when it comes to chloride versus water, chloride is oxidized. And so exception, chloride versus water, chloride wins, it is oxidized. In this case, we didn't have that, because there's something even better, potassium. Potassium is way better than either chloride or water. But if we didn't have potassium, then we'd have to competition between chloride and water. And who wins? Chloride, even though it's weaker. All right, so continuing on with the chart method here, the strongest reducing agent is potassium. And so all we're going to do is we're going to take them there. If I look at potassium, I have this equation. Potassium plus an electron yields potassium solid. This is backwards. This is wrong. I need potassium as a reactant, not as a product. So what I'm going to do is I'm just going to reverse this one so that potassium now is the reactant and potassium ions are the product plus an electron. Water I can just use as is. Water as the oxidizer is I'm going to have 2 waters plus 2 electrons. This is going to yield hydrogen gas plus 2 hydroxides. And then I'm going to cross multiply. And so this is 1 electron, this is 2 electrons, so we'll multiply the top one by 2. And the bottom one by 1, so I'll just leave it alone. And then just add these up. Adding these up, I'm going to get 2 potassium solids plus 2 waters plus 2 electrons yields 2 potassium ions plus hydrogen gas plus 2 hydroxides. Then I look for a driving force. The driving force I'm just going to base on the half reactions. The half reaction is the easiest place. So this is losing electrons, that's my reducing agent. This is gaining electrons, this is my oxidizing agent. And this is gaining electrons, this is my oxidizing agent, and this will be my reducing agent in the reverse direction. And so this is reducing agent, this is oxidizing agent, this is oxidizing agent going backwards, this is reducing agent going backwards. And so let's compare the 2 oxidizing agents, water versus potassium ions. Which one's stronger? So I see potassium ions here, and where does water belong? Yeah, and so which one's stronger? As an oxidizer. Water. Water's stronger. So I go back here. And let's put that in. Water is a stronger oxidizer than that, and therefore we have driving force. That means because of the conjugate relationship, the reducers must follow the same. But wait a minute, here. I have hydrogen gas. So can I say that gas formation is also a driving force for this? And the answer is no. Gas formation only works for metathesis reaction. It does not work for redox reactions. Same thing goes with precipitation. Precipitation is not a driving force for redox. The only driving force is stronger to weaker. And so there is actually a reaction. This reaction generates hydrogen gas. We reacted with well, what happened to sodium chloride? Do you see any sodium chloride in this reaction? No. And it turns out that sodium chloride, this is a trick question, sodium chloride is a spectator in this reaction. It doesn't react. All right, sorry, just one more reaction we're going to do. This one is a bit tricky here. And it's going to rely on skeleton redox and experience. That is your experience of certain chemicals, like ethanol. Ethanol, what's the formula? It's CH3CH2OH. Potassium permanganate is KMNO4, and hydrochloric acid is HCl. When we do this, it looks like there's a potential metathesis reaction here. If I look at this, what does this form? This forms HMNO4 and KCl. And there is a driving force for this. We're going from a stronger acid to weaker acid. Do you know the name of the weaker acid? What's the name of the anion over here? What was the name of the anion? Permanganate. It's an ATE, so it goes permanganic. This is permanganic acid. And so the 8 gets dropped and replaced with an ic acid. But there's a more significant reaction. And the more significant reaction is because you know the redox chart, and you know that permanganate is the number 5 most powerful on the chart. The number 5 most powerful. This is why you should look at the chart once in a while. The number 5 most powerful oxidizer on the chart. So if you have a powerful oxidizer, then you got to start worrying about other reactions occurring. And in fact, we did this reaction in lab. The reaction was we took solid potassium permanganate and mixed it with hydrochloric acid. When we take solid potassium permanganate and mix it with hydrochloric acid, do you know what you formed? Chlorine gas. In other words, the permanganate oxidized the chloride to chlorine, and we had a redox reaction occur. It didn't oxidize the water to form oxygen gas. It oxidized the chloride to form chlorine gas. But what's easier to oxidize? Water or chloride? What's easier to oxidize, water or chloride? According to the chart, water is easier to oxidize, but you know it is an exception, and therefore chloride's easier to oxidize. What's easier to oxidize? Methanol or ethanol, actually ethanol. Ethanol or chloride? What's easier to oxidize? Ethanol or chloride? Well, this is like when you oxidize ethanol, you're taking ethanol and reacting with, let's say, oxygen. Oxygen is the prototypical oxidizer. So if you take ethanol and oxygen, you burn it. So which one's easier to burn? Water, chloride, or ethanol? Have you ever tried to burn water? Maybe, but it's not going to be very successful, right? Have you tried to burn salt, table salt? Yes, I've tried to burn it. Did it burn? No. Have you ever tried to burn ethanol? Yes. Does it burn easily? Yes. And so ethanol is what we say electron rich. It's a powerful reducer. And so ethanol, this is the experience part. We've experienced, or many of us have experienced that ethanol is a good fuel. Fuels are reducing agents. Whereas water is not a great fuel and chloride's not a great fuel, ethanol is. And so this is the other thing in the inventory. And so I'm starting to think that there's going to be a redox reaction between permanganate and ethanol. But what we're going to do is we're going to use the chart method. And the chart method is we inventory. So our inventory is going to have ethanol, potassium ions, permanganate ions, hydrogen ions, chloride ions, and water. And then we know that ethanol is a reducer. Potassium ions are an oxidizer. Permanganate's an oxidizer in combination with H+. H+ alone is an oxidizer. Chloride is a reducer, and water is both an oxidizer and a reducer. And then we look for the strongest oxidizer. The strongest oxidizer is what? You have your choice. Potassium ions, like in sea salt. Are you worried about that? Water. Are you very worried about water? No. Acid, yes. I worry about acid, H+. I don't want to drink this stuff. But I'd rather drink acid than permanganate and acid. And so permanganate is going to be the strongest oxidizer, for sure, permanganate and acid. Okay, now as far as reducers go, ethanol is not on the chart, but we can compare it to chloride and water. So water is better than chloride, but ethanol would be better than both of them. And so this is it. Now, the permanganate and acid, we can just copy that from the chart. And so permanganate requires 8H plus 5 electrons. This is going to yield manganese 2 plus 4 H2O liquids. We just copy that from the chart. But what about ethanol? Ethanol is not on the chart. And so what do we do about ethanol? You combust it. When you combust ethanol, what does it form? Carbon dioxide and water. This is what we call complete combustion, complete oxidation. However, it is possible to get partial oxidation. This happened to me. I went camping. Some of you have probably heard this before, but I went camping in Joshua Tree. And when I went to Joshua Tree, I stopped in Yucca Valley and bought at the 99-cent store there, I think. And they had $1 bottles of Santa Barbara wine. So I couldn't pass that up, so I bought a $1 bottle of Santa Barbara wine to enjoy at the campfire. But when I got to the campground and started the fire and then opened the bottle of wine, it didn't taste very good. You know what it tasted like?
A $1 bottle of wine.
Yeah, and now I know. Now I know why it was $1. Because it was partially oxidized ethanol, and when we partially oxidize ethanol, it's like this. This is the symbol for oxidizer here. It can form something called ethanal. Ethanal is like formaldehyde. It didn't taste like formaldehyde, though. And so it didn't produce ethanal. It went one step further in the partial oxidation scheme of things. It went to CH3COOH. CH3COOH is acetic acid. So do you know what my wine tasted like? Vinegar. It was awful. I couldn't drink it. And so I used that bottle of wine to extinguish the fire. It was sad because that was a $1. Then it was expensive. It was so cheap. I thought I got such a great bargain, and then it turned out to be.
What year was this?
This is so long ago.
Roughly.
This was roughly.
Pre or post 2000?
Hmm?
Pre or post 2000?
It was post 2000. I think it was around 2006 or 2007. Probably about 2006, maybe. But anyway, this stopped here. I wish it further oxidized, not to carbon monoxide, because if it further oxidized to carbon monoxide, I wouldn't be here right now. I wish it had further oxidized to CO2. If it oxidized all the way, that is, if I had complete oxidation, then I'd have sparkling grape juice. Sparkling grape juice would taste a lot better than vinegar. But unfortunately, it didn't go all the way. So what we're going to do is we're going to assume it goes all the way for us. That is, we're going to assume complete oxidation. And so let me add another page here. And then we're going to use skeleton redox. So assume complete oxidation. And then we're going to use skeleton redox to figure out what's going on. And so what we're going to do is we're going to do CH3CH2OH, and this is going to go all the way to CO2 gas. Skeleton redox, what we do is we balance all elements other than hydrogen and oxygen. So on the left here, I have two carbons from the ethanol. On the right here, I only have one carbon. And so to balance this, I need to change the coefficient here. So I'll make this 2. So now I have 2 carbons on both sides. After the carbons, I balance the oxygens. So on the left here, I have 1 oxygen. On the right here, I have 4 oxygens. So I'll need to add 3 oxygens. No, I can't add oxygen. Do you know what I have to add? Water. I'd like to add oxygen. But oxygen is not what we add. We add water. And then after the oxygens are balanced, we balance the hydrogens. So over here I have 3, 5, 6, plus 6 is 12 hydrogens. And on the right I have no hydrogens. So I add plus 12H plus. And then I balance out the charge. So the charge on the left is 0 plus 0 is 0, and 0 plus 12 is plus 12 by adding electrons. So there's going to be 12 electrons here. So this is an oil. Oxidation is lost. So the ethanol got oxidized. Who oxidized the ethanol? Well, it's got to be the permanganate that oxidized the ethanol. This is going to yield 2 CO2s plus 12H plus 12 electrons. Now this is the oil, the balanced oxidation half reaction, or is it balanced? So let's just check for balance. When we check for balance, we check that the atoms are balanced. So 1, 2, 2 carbons, 3, 5, 6, plus 6 is 12 hydrogens, 1 plus 3, 4 oxygens, 4 oxygens here. So the atoms are balanced. Then we check charge balance. 0 plus 0, 0 plus 12 minus 12, 0. So 0, 0. So this is balanced. This looks good. So then next I combine the 2 half reactions by cross multiplying. I cross multiply by the number of electrons. And so up here I had 5 electrons. So I'll multiply the bottom equation by 5. And down here I had 12 electrons. So I'll multiply the top equation by 12. And so I'm going to go ahead and do that here. And so just about done. 12 permanganates plus 8 times 12 is what, 96? 96H plus 5 times 12 is 60. So 60 electrons plus the ethanol was 5. So 5 times 1 is 5 ethanols. And then how many waters did I have? The ethanol. 3. So 3 times 5 is 15. All right. Move that up. Okay, then this is going to yield the products. So then I had 12 Mn2 plus. And then I had 8 waters, no, 4 waters. 4 times 12 is 48. It's 48 H2O liquids plus how many CO2s did I have? 2 times 5 is 10 CO2s plus 60 H plus 60 electrons. Then we look for driving force. The driving force for this is my oxidizer here. This is my reducer here. And then if I go to the half reactions, we can see here, if this is my reducer here, then the other side will be my oxidizer. And likewise, up here, if this is my oxidizer here, then the opposite side will be my reducer. Here. And so I can label this in the main equation here. Manganese and water, this will be my reducer. CO2 and H+, this will be my oxidizer. The problem is that not all these are on the chart. And so we're going to have to use experience to dictate it. What's a stronger oxidizer? Permanganate in acid or carbon dioxide? In other words, in acid. So we'll get rid of the acid. What's a stronger oxidizer? Permanganate or carbon dioxide? If you have if you inhale carbon dioxide, are you going to get much damage to your throat and lungs? No, I mean every breath you exhale carbon dioxide. Does it cause much damage each time you exhale? No. If you were to eat permanganate, do you think that's going to cause damage? Severe damage, yeah. And so this one is just based on experience. Obviously, permanganate is way stronger. CO2 is extremely weak. And therefore, we have driving force. And the reducing agents are going to follow the same pattern, strong to weak. And so driving force is present. If driving force is present, then what we're going to do is we're going to try to simplify this, and then we'll be done. So the 60 electrons cancel. The electrons have to cancel. If they don't, then we did something wrong. The H pluses end up canceling. I have 60 H pluses on the product, so I'm going to cancel 60 of the 96. That's going to leave me with 36. In the waters, I have 15 waters here. I'm going to get rid of 15, so this is going to give me 33 waters there. And it looks like nothing else cancels. So altogether, this is what I'm going to have. I'm going to have 12 permanganates plus 36 H plus 5 ethanols yields 12 manganese 2 plus 33 H2O liquid plus 10 CO2 gas. And this would be the reaction spec. So we don't need oxygen to burn things or to oxidize things. This could easily result in a fire here, but so you got to be careful because permanganate's more powerful than oxygen. We're all right. All right, so this is it for this chapter here, and then what you're going to do is you're going to just continue the equations. You should start the equations for experiment 18. Those are all redox for the most part. All right, any questions? Yeah, I'll stop here. I went a bit longer than I was hoping.